Thanks everybody for coming today to the first Philosophy Club event of the semester. We're really happy to have James Reed and Tushar Menon. They're graduate students from Oxford who are visiting at the University of Illinois in Chicago. We both work in philosophy of science and on space-time, so we're really interested to hear them tell us a little bit about space-time. What is it good for? So thanks very much.
Thanks very much. Yeah, so as John said, a lot of my work and Tushar's work is in the philosophy of space-time. So we want to tell you a bit about this in the particular context of relativity theory. So the kind of questions that are going to interest us today are things like, what's the ontological status of space-time in relativity theory? Or in what sense does space-time explain the behavior of matter in relativity theory? So the way it's going to pan out is I'm going to introduce you to special relativity and then to some of these questions in that particular context. Tushar is then going to take over and talk about these things in the more nuanced and difficult context of general relativity. So, by the way, if you have any questions throughout, just ask. Don't mind fielding questions throughout. So let's start slow. So here is a train. And it looks from the picture like the train is moving either pretty slowly or maybe it's stationary. Compare it with this train, which is clearly belting along. So ask yourself the question, if I was sitting in one of those trains and I weren't looking out of the windows and I ignored the kind of mild jostling from the train moving along the tracks, would I be able to tell which of these two trains I was in? And on reflection, it seems like the answer is no. So this observation has been known for a very long time, at least since Galileo. And in fact, Galileo gave a really beautiful expression of this point. So I'm going to read it to you in full because I think it's so nice. And then we'll reflect on it in modern language. So this is what Galileo says. He talks about ships rather than trains, but the same point stands. So shut yourself up with some friend in the main cabin below decks on some large ship, and have with you some flies, butterflies, and other small flying animals. Have a large bowl of water with some fish in it. Hang up a bottle that empties drop by drop into a wide vessel beneath it. With the ship standing still, observe carefully how the little animals fly with equal speed to all sides of the cabin. The fish swim indifferently in all directions. The drops fall into the vessel beneath, and in throwing something to your friend, you need not throw it any more strongly in one direction than another, the distances being equal. Jumping with your feet together, you pass equal space in every direction. When you have observed all of these things carefully, now have the ship proceed with any speed you like, so long as the motion is uniform and not fluctuating this way and that. You will discover not the least change in any of the effects named, nor could you tell from any of them whether the ship was moving or standing still. In jumping, you will pass on the floor the same spaces as before, nor will you make larger jumps towards the stern than the prow, even though the ship is moving quite rapidly. The droplets will fall as before into the vessel beneath without dropping to the stern, although while the drops are in the air, the ship runs many spans. The fish in the water will swim towards the front of the bowl with no more effort than towards the back, and will go with equal ease to bait placed anywhere around the edges of the bowl. Finally, the butterflies will continue their flight indifferently towards every side, nor will it ever happen that they are concentrated towards the stern as if tired out from keeping up with the course of the ship, from which they will have been separated during long intervals in keeping in the air. So I think the point is clear. If you were in such a ship or such a train and you didn't look outside and you were just looking at your local physics, you wouldn't be able to tell what velocity you were moving. So we can express this in modern nomenclature. So let's call the inertial frames the systems of reference related by uniform velocity shifts. And then we'll say that the relativity principle says that the laws of physics take the same form in all inertial frames of reference. So this is basically just an expression of the point that I've just made. This was known since Galileo, but it's a cornerstone of Newtonian physics, and it's also a cornerstone of relativistic physics, as we'll go on to see. So we'll come back to the relativity principle in a couple of minutes, but now I want to talk briefly about an apparently different topic, which is electromagnetism. So around the end of the 19th century, arguably the third greatest physicist of all time, behind Newton and Einstein, i.e. James Clerk Maxwell, cooked up a theory of Electromagnetism, which was a unified theory of electricity and magnetism. The theory is actually super simple, so you could write it in two equations. We don't need to worry about what these guys mean, but they're called Maxwell's equations, and we can derive loads of crazy results and interesting results from them. So one of the most striking things that you can derive from this, it takes about a couple of pages maybe of algebra, is that Maxwell's equations tell us that the speed of light is constant, and in physics it's normal to call this speed c. So it's worth reflecting upon how weird this is. So imagine if I was standing here and Tushar were behind me and he shines a torch past me, then I would see the light traveling at c. But now imagine that I'm on a really fast, say, spaceship and I'm traveling 99% of the velocity of c. Then you might think that because I'm going pretty much the same speed, it would look to me like light is going past me really slowly. That would be like what you would expect from thinking about cars on a highway, for example. But in fact, something different happens with light. Even if I'm going 99% of the speed of light, I would still see the light going past me at c. So the speed of light is the same in every frame of reference. That's, yeah, certainly a crazy thing. So it was only really Einstein in 1905 who just fully took this on board when he wrote down his theory of special relativity. So the special theory of relativity is actually very simple. It consists in two postulates which we're now in a position to articulate. The first is just the relativity principle that we saw before. The laws of physics are the same in all inertial frames of reference. And the second is the so-called light postulate. The speed of light takes a fixed value that is independent of the speed of the source. So a lot of special relativity is just really exploring the consequences of these two postulates using pretty much high school maths. Like a lot of it's just Pythagoras' theorem. So I'm going to go through a few of these weird results for you now. So one of the best known special relativistic effects is so-called time dilation. So the motto is that moving clocks tick slower. Time runs more slowly for moving things. There's an easy way to think about this using a very simple clock, which is called a Langevin clock. So this is a clock which is built out of two mirrors, a top mirror and a bottom mirror. Then imagine that there's a ray of light bouncing between the two mirrors, and imagine that the clock ticks every time it hits the bottom mirror. So it goes something like bounce, tick, bounce, tock, bounce, tick, bounce, tock. So if it was in a stationary frame of reference, that's what it would be doing. Now imagine that the clock is moving uniformly, say to the side. Then you can consider what the light would do if it were moving like that. Think about the light again. It was going to go bounce, tick, bounce, tock. Because light is traveling at the same speed, but now it has a longer distance to travel. It not only needs to go up, but it also needs to go along a bit because the clock's moving. That means that the time between ticks is going to be slower for a moving clock. Now, we illustrated this with a...
All right.
Yeah, sorry.
Yeah,
Go ahead.
so saying that with the time, the reason why it's moving slower is because it has a longer distance to cover, is that?
Right.
Oh, all right.
Simple as that. And on the assumption that it travels at the same speed at any frame.
Yeah. Okay, so essentially light travels at a constant speed, but depending on the distance, it might appear faster or slower. So
That's what I'm saying, yeah.
all right.
That's why the time on the ticks is slower for the moving clock.
All right.
So you can actually, if you want to work it out, it's really only a few lines on a page. This is the exact formula for how the speed of the moving clock is related to the speed of the stationary clock. We have a factor of velocity here, so if this guy were bigger, then I would have a number smaller than 1 on the bottom, so I would get a number bigger than 1 out the front, and that would tell me that the times of the ticks of the moving clocks, between the ticks on the moving clock, was bigger than the time between the ticks of the stationary clock. So we illustrated this with a very simple light clock, but it generalizes to all clocks. And this is the result known as time dilation. The motto, moving clocks run slow. It's important to be aware of the kind of relativistic aspect here. So if I see the clock moving, it looks like the clock is ticking slower. But now imagine that I'm kind of sitting on top of the clock. Then it would look like the clock is stationary relative to me. And then I would see the clock ticking at its original rate. So what we have to conclude is that time between ticks on a clock is not an objective fact, but it's somehow relative to a frame in special relativity, which is not something that we had in pre-relativistic physics. Yeah.
Okay, so in other words, like this relativistic frame it didn't incorporate distance, how that could affect the speed of light. Is that what you're saying?
So what I was saying with the light clock is the speed of light is always the same, and because the distance it has to travel is longer, that means that in this very simple example of a clock, the light time between ticks is longer. Now, the mechanism for other clocks might be more complicated, but you'll always find that moving clocks run slow. So that's just one of the examples of special relativistic weirdness. I want to mention two others for you. Again, you can do quite simple calculations, and you can look. So imagine that you have say, a meter ruler in front of me, or a yard ruler. Then it looks like a yard in front of me, but now imagine that it's being boosted, so it's moving past me. Then what we'll find is that moving rods are contracted. So to me, it looks like the moving rod is contracted, but again, if I was sitting on it, it would look like it was stationary, so it would look like a yard. So there's no objective fact about lengths and distances. Again, it's all relative to a particular frame of reference. This phenomenon is known as length contraction. And the last one I want to mention for you is the relativity of simultaneity. So maybe this is even the craziest. So what counts as simultaneous with a particular event is relative to a frame of reference. Whereas before, like intuitively would have thought that whether two events are simultaneous is an objective fact in the world. So there's a very easy way to illustrate this. So imagine that I'm sat right in the middle of a train carriage and have a torch in either hand. So these are the torches. If I turn the torches on at the same time, then the light comes out here, and it hits the back of the train carriage, and it comes out here, and it hits the front of the train carriage. But now imagine that the train carriage is moving. So this is how things would look for someone, say, sitting on the station rather than on the train. Again, I'm here with my two torches. Turn them on at the same time. The light comes out the back, but of course the train is moving, so the train moves forward to meet the light, and the light ends up hitting here. Whereas the light coming out the other end, the train is going to move away from the light. And so what we find is that if I'm looking at the train carriage moving, it looks like the light hits the back of the train before the front of the train. So in this particular frame in which the train is moving, the event of the light hitting the front and the back, events of the light hitting the back and the front of the train are not simultaneous, whereas they were simultaneous in the frame in which you're sitting on the train. Does that make sense? Yeah.
So, in the first frame,
yeah,
would we want to say that the hitting of the light at the two ends is simultaneous from his standpoint? Because what he sees is the light coming back, right? And so that sort of cancels the effect of moving forward.
Yeah, that's a very astute point. So, but I mean, you could still think, I mean, surely there is a fact of the matter about whether these two hit each other or not. Whether you could empirically know that is a much more subtle business. So well taken, but I don't think it erases the point. I think there was another hand, or?
I had another point.
Okay. So now we can start asking some philosophical questions. So what's the explanation for these weird special relativistic effects? Now, one thing that people often say, and in fact it might be the dominant explanation, is that these things have something to do with space-time. So people will say, space-time mumble mumble, space-time mumble. So what we want to do is explore the kind of reasoning that's going on here. To do this, we'll require just one more slide of setup. So I said that the time between ticks on a clock was not a frame-independent fact anymore in special relativity. I also said that the length of objects was not a frame-independent fact. But it turns out if you take this combination, which is essentially the spatial distance between two events minus c squared, all squared, minus c squared times the temporal distance between two events. So imagine that I'm here at one time and over here at another time. So you take the spatial distance between these two events minus c squared times the time I was sitting here versus the time I was sitting here. Then this so-called interval is actually a frame-independent thing. You might not have expected that just from what I've said, but you can work out that it is. So this is where people start talking about space-time. So I don't know how many of you know about multiplication of matrices. I'm not going to go into it, but basically you can take this thing and you can write it in a more complicated way, in which we have this matrix sitting in the middle. And people will say that this matrix represents space-time in special relativity. So just to summarize the dialectic up to this point, we started off with Einstein's two principles, the relativity principle and the light postulate. We derived a bunch of strange special relativistic effects like time dilation and length contraction and the relativity of simultaneity. Then we found that there was an interval which was actually frame independent, unlike ticks on a clock or lengths of objects. And then we extracted some mathematical object which is supposed to represent space-time somehow. So this dialectic started off with dynamics really, and it derived something about space-time at the end. So you might be surprised when I say that most people kind of reason in the opposite direction. They say somehow space-time explains the way that stuff moves. So here's a very famous philosopher, Tim Maudlin from NYU, who says something just like this. So he says, if we accept that in a vacuum there is no physical structure except for the structure of space-time itself, then the behavior of light in a vacuum implies that the geometry of space-time alone determines the trajectory of light rays. That is, given any point in the space-time P, the structure of space-time ought to fix where the light emitted from that point will go. If you're confused, you're not alone. So this is another famous philosopher called Harvey Brown, who says it's wholly unclear how this geometrical explanation is supposed to work. So we can summarize the two views of these guys as follows. First, we have what I'm going to call the geometrical approach. This is as advocated by Maudlin. And second, we have with a dynamical approach, which is pretty much what's advocated by Brown. So for Maudlin, special relativistic phenomena are explained by matter being embedded in this so-called Minkowski spacetime. Whereas for Brown, special relativistic phenomena are explained by the dynamics of matter. Now, it should be clear to you at this point that I think that the second option is better. I started off with facts about the dynamics and I derived something about spacetime. It was totally unclear what, if any, causal or explanatory work that alleged spacetime structure was doing. But it's worth flagging that this is, for whatever reason, the minority view. I guess people have the idea that stuff sits in spacetime and somehow it constrains the way that it moves, but it seems to me like metaphysical fluff. But it will be worth talking about.
I'm really confused right now.
Okay.
Okay, so essentially, space-time is essentially the physical shape of reality. Is that what we're saying? Or? No?
No, so the question is, why do we have effects like time dilation and length contraction?
Okay.
And some people say it's to do with space-time.
Right.
Others say, no, we start off with those effects, they follow from Einstein's two postulates, and we derive something about space-time, starting off with those effects. So I guess it's a question of the arrow of explanation, whether you think the dynamics come first and you derive facts about space-time, or whether you think space-time comes first and you derive facts about dynamics. The former view is the view advocated by Maudlin, and the latter view is the view advocated by Brown.
Okay.
So Tushar is going to go over this a lot more, and we can certainly discuss it a lot more as well. In fact, I just have one more point to make on my section. So, Brown not only says that the dynamics of matter is prior to facts about space-time, but he in fact embraces a stronger ontological thesis. He's kind of a modern strand of what you would call a relationist about space-time, someone who thinks that facts about space-time are reducible to something else. He says the appropriate structure is Minkowski geometry in special relativity, precisely because of the laws of physics. So you start off with the laws of physics and you derive facts about Minkowski space-time structure, but there's nothing ontologically privileged about that guy. Whereas Maudlin is going to want to say space-time is something out there in the world and is somehow causing us to observe these special relativistic effects. Great, so that's all I wanted to say in the context of special relativity. Tushar is going to go over these things again, so hopefully things will become increasingly clear.
If you do have any questions, do you mind fielding a question for just a second? I need to get my cheat sheet, which I left in the office.
No problem.
Sorry.
Yeah.
So if we can describe it using that formula that you just mentioned, doesn't that imply that if there's something out there that we can observe and describe using a formula, is that enough to justify its existence?
So you're thinking of this interval formula up here.
Yeah.
So I mean, this is just facts about the distances and times between events. Like, it seems to be, first of all, a step to read off ontology from that. It doesn't seem to be mandated that you read off this particular mathematical structure as being something out there in the world. And second of all, it doesn't seem to be necessary to read off any kind of explanatory role. Like, at least there's a story to be told about how this guy is or there needs to be more needs to be done to explain how this guy is causing us to observe special relativistic effects. It's explaining special relativistic effects. And I guess those are the two things that Brown would dispute. Perhaps, does that answer your question or not?
I don't think it does.
So, can you repeat the question?
It's like, so if we're, like, for example, like gravity, right? There's a formula for how gravity works on Earth, right? And like the speed at which it goes. So we're able to make a formula for an observation that's occurring on Earth. So this is a formula for how you can relate to events. Isn't that enough to say that there is something that we're describing, so therefore it exists?
So, I mean, you start off with formulae for describing, I don't know, the behavior of special relativistic rods. And you do that for maybe rods made out of loads of different types of matter. And then we end up boiling this interval out to something which is kind of universal across all of those laws. So I agree that in the initial laws, like maybe the laws saying there's electrons in the world that behave such and such, so we should believe that electrons exist. But what Brown says is that this guy, this Minkowski metric field, is just a codification of the universal behavior of the dynamics of matter. So he would agree with you regarding the initial dynamical laws, but he wouldn't think that there's anything special about this guy, which is just meant to be here.
So it's like a description.
Yeah, exactly. Yeah. Cool. So, yeah, over to Tushar in general relativity.
Thanks, James. And actually, this does set it up sort of quite well for the sorts of things that I wanted to talk about. So, in terms of kind of weird consequences of relativity, you can't really beat general relativity. I mean, special relativity is kind of a warm-up. But I'm not going to go into any of those. Largely because I think if you haven't come across relativity before, special relativity is kind of enough. But it does. The reason that it's interesting to think about general relativity is because it's our best theory of gravitation, and it's also ostensibly our best theory of space-time, in scare quotes, whatever that thing might be. And as James has just said, we have reasons to be skeptical of the claim that we can sort of start off with space-time first, and then chuck all of our matter fields into it, and somehow expect space-time to tell the matter fields what to do. I mean, I'm using quite crude language because really it's not quite a causal story, but for the purpose of caricaturing a position that I don't agree with, it's perfect. But to be serious, I'm going to give the geometrical approach possibly a bit more credit. There's a lot more going for the geometrical approach in general relativity, and we'll see exactly why that is as we continue. So if you've ever come across anyone talking about general relativity, or if you've read some popular science about general relativity, or if you've just gone to university and studied the physics, you'll find this kind of metaphor all over the place. The idea is, what general relativity tells you is that gravity is not a force that acts between sort of two distant particles that have a particular mass. There's no force at all. What's actually happening is that space-time itself is curved. What causes the space-time to curve is the presence of mass, and then because of the effects of that curvature, we now reduce the gravitational effects to spatiotemporal effects. And in light of the kind of stuff that James was talking about, you might be skeptical of that. If space-time in special relativity doesn't obviously tell you why matter fields behave in a particular way, it seems like more of the same kind of problem to think that in general relativity, space-time will tell matter what to do. So that might seem kind of obvious, but there's still a lot to be filled in over there. I think I want to frame my section of this talk by sort of coming back to this picture at the end, with the hope that by the time we're finished, we'll see really what's wrong with this picture. Because it's quite a compelling way, I think, to think about the world. But I should just put in a quick aside about this metaphor. You find this metaphor all over the place. It's a bowling ball and a trampoline. That's kind of what gravity is. And one of the sort of superficial problems with this is it actually doesn't portray space-time geometry in the way in which it's actually thought of in general relativity. The idea being, if you think of a trampoline, or if you think of a rubber sheet, it's a two-dimensional surface. And if you talk about curvature, the idea is that it curves into a third dimension. And so you might think that in order for something to be curved, in order for a surface to be curved, there needs to be a high-dimensional space in which that surface is embedded so that it can curve into that. Turns out that that's not true. That's just an incorrect way of thinking about abstractly and also physically, concretely, what's going on with curvature. But that's not the important reason why this isn't a good picture, and we'll work towards why this isn't a good picture. So coming back to some of the questions that have already come up, there is this temptation when we write down a physical theory. So, for example, the kind of thing that James had earlier, which was a simple way of writing down Maxwell's equations. We have this compulsion, which is sort of fairly well-founded and quite justifiable, to think, well, if I'm writing down a theory of physics, and my theory of physics says, there's some object that I'm going to represent by J, which in this case is something like a current density, and some other object which is going to be related to an electromagnetic field, then there's a fairly straightforward representational relationship between the things that I write down and the things that are out there in the world. This is the electromagnetic field, modulo some complications. This is a charge density, and all is well. So I've written this down, and according to my best theory, these are the things that are out there in the world. And it seems like if you're going to try to figure out what things are out there in the world, it seems like fundamental physics is a good place to start. So that seems fine. It seems like we've got some kind of ontological commitment to whatever this F represents and whatever this J represents. But in a sense, that's kind of a naive way of thinking about what an ontological commitment might be. So it, for example, doesn't tell you whether if I took this away, I'd still be able to legitimately talk about this. Or similarly, if I took this away, if I lived in a universe that didn't have one of these, would this sort of object still exist in that universe? And this goes under the discussion in metaphysical circles, it goes under the title of ontological dependence. The idea is something like, if I can write this down without having to specify any other fields, then this object is ontologically independent of those other fields. And if it's the case that in order to write down, when I write something down, its very existence requires the existence of something else, then that something is ontologically dependent on something else. And you can sort of see from the last quote that James gave you from Harvey Brown, that Harvey embraces an idea of ontological dependence when it comes to space-time. Because what Harvey wants to say is that when you write down your equations for matter fields, there's some structure that's inherent in those equations. There's something about the way those matter fields behave that's universal across a whole lot of different matter fields. But if you take the matter fields away, it's not like you're going to leave the scaffolding behind. It's not like you're going to leave that structure, that common structure behind. So you've got a notion of ontological dependence of space-time. And that seems to be doing kind of a little bit of heavy lifting in Harvey's way of thinking about, or at least in a first pass at understanding Harvey's way of thinking about space-time. But you might think, well, there's a bit of a problem with this if you take this bowling ball metaphor seriously, or even better, if you think about gravitational waves, which were recently discovered. Gravitational waves are sort of sold to you as things, as ripples in the fabric of space-time. They're ripples in this metric field. And so you might think, well, general relativity is committed to an ontologically independent metric field. So surely now that we've got an ontologically independent metric field, that's the metric field that's going to define your notions of length and time, and all of the weird relativistic, special relativistic effects that you had when you had an ontologically dependent metric field, but with a few added things. And you'll see that this isn't quite the right way to think about the metric. So just to remind you, so James wrote something like, I'm running out of, I didn't think this through. But anyway, X, Y, Z, T, right? Sorry? Deltas and C's and yeah. It looks something like this, right, with zeros elsewhere. And so the idea was, well, we've got some facts about how dynamical fields behave, and we can write it in a particularly perspicuous way. We can write down the invariant interval, and then just point to a thing on the board and say, that thing in our theory is the thing that represents space-time. And we can see that in this ontologically dependent story, it's kind of guaranteed. We've kind of stacked the deck already. It's guaranteed that measuring devices built out of this matter will give us lengths that correspond to the space-time structure that's given by this metric. So you might think that one thing that a metric does is it allows you to just write down your dynamical laws. It plays a role in articulating the dynamics, which is to say you can't write down your dynamics without giving some information about what metric structure is. But there's a second role that the metric could play, and this is the kind of role that people would like the proponents of the geometric approach to general relativity might want you to think that the metric in general relativity plays. And that role is in addition to being able to allowing you to articulate dynamics, it also constrains the dynamics. And I sort of emphasize constraints because that's the bad word. We don't want to think of space-time as constraining dynamics. But it seems like a perfectly reasonable thing to ask whether a metric can play that kind of role. And so it's useful to, sorry.
No, it's just so if I understand what you're saying about the math thing from before, is that because we're able to get a math equation down, that implies there's some kind of structure between those two things. Is that what
sorry, between which two things?
The two whatever those things, those equations are for
these.
Yeah, or that one up there.
Oh, yeah, okay.
There's some kind of underlying structure. We don't know what it is, but there is some kind of...
That's right. That's right. There's some kind of underlying structure, but it's unclear when we just write this down whether that underlying structure is ontologically independent or ontologically dependent on the things that we write down. So the point that I was trying to make was, so for example, it seems perfectly reasonable for us to be able to write something. I mean, I can tell you it is perfectly reasonable for us to write down something like this, right? So we can say that at least in the context of articulating something about the relationship between F and J, F is ontologically independent of J, whatever those things are.
Ontologically, what does that mean?
It means that if J doesn't exist, F can still continue to exist. The mere existence of J, the mere existence of F does not require the additional existence of J.
So it's like necessary and sufficient conditions.
Exactly.
Okay.
Exactly. And so what I'm saying about space-time on Harvey Brown's sort of admittedly slightly extended reductionist view is that the thing that we write down when we write a spatiotemporal interval like this and this is what James called eta, which was the metric. That metric is not something you can just write down on its own in the absence of other dynamical fields. That's the ontological dependence claim.
Oh, so there's something else that allows us to write that math.
Exactly.
Okay.
Exactly.
So the trick. Okay.
Yeah.
So
So
your argument is basically that there's an implicit assumption that there is an interdependence between them, and for that reason, we can't say that they represent something because they might be able to exist without each other.
Yeah. So the idea is that the maths isn't sort of just writing this on the board is not nuanced enough to give us a distinction between those two things. That's correct. Right.
So just to repeat, so for Harvey Brown, the metric field in special relativity is ontologically dependent on the behavior of matter out of which the stuff in this room is built, etc. And the claim is that in general relativity, maybe the metric field isn't ontologically dependent in the same way.
Yeah, that's exactly it. So the idea is, because we've got things like gravitational waves and this sort of pre-theoretic picture of the metric being a rubber sheet, you might think, well, I just take all my matter away and I still have that rubber sheet, I've still got those gravitational waves. So now suddenly my metric is ontologically independent. And once I have a metric in my theory, then I've got a notion of distances, right? That's the job of a metric. You've got a metric, you've got distances and time intervals and things. But that kind of papers over an important fact, which is you might have a metric in your theory, but that doesn't guarantee that it's going to be the metric that you measure, right? Just because you've written down something, you've written down an equation on the board, it doesn't mean that that equation is going to correctly describe the world. Moreover, even if you've written down an equation that does correctly describe the world, it doesn't mean that all the objects in that equation will play all the roles that those objects can play. Sometimes they'll only play some of those roles. And this is the point that I want to get across about how the metric works in general relativity. So just coming back to those two roles, it seems like the advocate of the dynamical approach is perfectly happy to say that the metric plays a role in articulating the dynamics, as here. But they'll stop short of saying, but it constrains the dynamics to obey that metric. Whereas the advocate of the geometrical approach wants to say, there's this extra thing. The metric in general relativity does constrain the behavior of matter. So this is basically what I already wrote on the board. I wasn't sure if I would be able to write on the board, which is why I have it on the slide. Right. So now so in general relativity, we've got what's known as a dynamical metric. A simple way to think about what a dynamical metric is, or a dynamical object in general, is it's an object that can take on different configurations in different possible worlds. So for example, this Minkowski metric is not a dynamical object, because whether we're in this world or some other possible world, if we're talking about electromagnetism, it's always going to take the same value. It's always going to be diagonals with ones and a minus one on it. Whereas the metric of general relativity is allowed to vary depending on sort of various contingencies. And the way that we encode how the metric varies is given by Einstein's field equations. It doesn't really matter sort of exactly what those things are. The G sub AB is the same as the G up there. The R is a measure of intrinsic curvature, and the T represents the mass and the energy momentum of matter. So basically what this equation is telling you is that there's some metric, some ontologically independent metric, and the way that that metric is in a particular world is governed by what the matter distribution in that particular world is. But it seems odd to say, if we've got a bunch of matter fields even in a general relativistic universe, it seems odd to think that the ontologically dependent metric that we had earlier from special relativity has somehow disappeared, right? We have a bunch of matter fields. Those matter fields have a kind of innate metric structure. But now all this time we've been talking about an ontologically independent metric. How do those two link up? A universe that looks like this. This has within it some particular specification of what that metric structure is. Now it might turn out to be the same as the ontologically independent metric. But the important point that we're trying to push over here is that it's not necessarily the case that they're the same. So this is just to reiterate what I said earlier. Just because you have a metric in your theory, it doesn't mean that it's going to do all the things that a metric does. And specifically, it doesn't mean that it's going to be the metric that's surveyed by rods and clocks. By surveyed by rods and clocks, what I mean is that it's not going to be that metric that defines your notions of length and distance and time. What is going to determine your notions of distance and time, hang on, let me go back, is going to be this metric. It's always going to be the ontologically dependent metric of your matter fields.
So is the ontologically dependent metric, or independent metric, is that like an axiom or something?
Yeah, I mean, it's a postulate of general relativity, that there exists this field that has these properties. That's right.
So we got general relativity, which we derive to get that metric right there, and then we derive other things from that metric?
Yeah, so general relativity tells us that we've got this metric,
Okay.
and this metric obeys some equations. Separately, we've got within, on some other matter theory, we've got some dynamical equations, and those dynamical equations might include references to this metric, right? This metric might still play some role in articulating those dynamics, but it doesn't, just because it plays a role in articulating those dynamics, it doesn't mean that the ontologically dependent metric of those dynamics is going to be the same as this.
Oh, so in other words, it may not necessarily line up. It might seem similar, but
Yeah.
may not have anything to do with this.
It might have nothing to do with this.
All right.
It might have something to do with this in special circumstances, or something like that. But the idea is, if it has something, if these two things happen to coincide, that's all it is. It's happenstance. It's not guaranteed by either the matter fields or the form of the Einstein field equations.
And so at the end of the day, these are just equations to describe the universe, pretty much.
Yeah.
Right? And we're just wondering, so this one seems like to be a pretty accurate equation, and we can see similarities in other dynamic equations that describe the universe,
Yeah.
but they may not have anything to do with
They
it.
might not line up.
They might be similar, but not the same thing.
Yeah.
Is that
Yeah.
okay?
The object that's picked out by things that look similar might not be the same object.
Okay.
The same mathematical object. That's right. That's exactly right. I mean, in a sense, that's basically all I wanted to say. That's kind of the whole point of the dynamical approach in general relativity, where even though you don't have this idea of ontological reduction of a metric to the main metric of that theory, it doesn't mean that you don't have an ontologically dependent metric, which is actually telling you how rods and clocks behave. So I'm going to end with the moral of both James's and my halves of the talk, which is, it just doesn't seem right. It's not right to say space-time tells matter how to behave. Space-time doesn't tell matter. It doesn't tell rulers how to behave. It's the rulers. It's the things that you use to measure sort of various things out in the world. Those are the things that determine what the structure of space-time is. And so now I'm just going to finish by coming back to the picture that I started with, and say, well, now it should be sort of fairly clear what's wrong with thinking about the world, with thinking about the world of general relativity like this. If we think space-time is the kind of thing that can have an effect, if you think that space-time is the kind of thing that constrains the dynamics of things embedded in it, then this works perfectly well. But as we've discovered, it's not space-time, it's not the metric of general relativity that does it. It's the ontologically dependent metric of whatever dynamical equations govern the thing in space-time that tell you how your rods and clocks and various other things are going to behave. And with that in mind, I think it's good to be skeptical about claims that you might derive from thinking about the universe as looking like this. And I think with that, I'm basically done. So thanks.
We're delighted to field questions, and
Yeah.
got lots more to say.
Okay, so this has kind of the flavour of discussions in the philosophy of science about realism. So where do you guys stand on the old problem of, does science tell us that electrons exist?
Do you want to go first? So I fall on the realist side, but with caveats, as any good philosopher.
So I would say that I would be a realist about anything that I need to articulate my theories of physics. So in electromagnetism, I need this F field to describe the way that we observe electric and magnetic phenomena. But I don't need, it turns out, at least in the special relativistic context, a metric field. So I guess I'm kind of a restricted realist. I'm a realist about what I actually need to do physics.
Okay, so in this case, we would prefer to avoid the old tenet of take the least amount of axioms, if you will, to explain what you want to say. Where in this case, that maybe would, correct me if I'm wrong, maybe that would include taking the Minkowski spacetime as a postulate and then deriving however many, physical relationships that we want. Why would we avoid that in this case?
It kind of depends on what you want to do with your theory, right? The Minkowski metric is incredibly useful, but so we don't want to get rid of the Minkowski metric in our formulations of special relativity on practical grounds, right? If we say that it's a postulate of special relativity that spacetime is Minkowskian, and that's completely true, in addition to being really useful. But of course, the equivocation is then on sort of what you mean by spacetime. But as philosophers, when you're interested in trying to figure out what, for example, ontological commitments are, or what the most perspicuous way to write down a theory is, in such a way that the stuff that you write down corresponds to the kinds of things that, as James said, you ought to be a realist about. In those cases, in special relativity, it seems preferable to be a so-called eliminativist about the Minkowski metric. Say that it's just a useful piece of sort of codificatory mathematics, but I'm not going to endow it with a kind of metaphysical oomph that I might be otherwise tempted to.
Can we go back to the slide with the moral? Because I just wanted to jot that down real quick. Thank you.
I kept switching between rulers and rods and clocks. I hope it's...
So one way to think about metric fields, which maybe we should have mentioned, is, you can imagine a map, but take the grid lines off. Then you don't have a notion of distances or angles between any 2 points on your map. You can basically imagine your metric fields to be the grid lines. And then I guess Tushar's point in general relativity is there's this object G which could give you grid lines, but there's no guarantee that the distances that you read off with your physical rods and clocks actually align with the distances as given by that other object.
Yeah, that's good.
So if there was some theory that someone came up with that kind of like merged these two things so that they would show how they relate to each other, then would you guys be willing to accept the fact that space-time is an actual thing, or would you still have?
Yeah. Basically, so what the dynamical approach is a call for either a story that does exactly that, or in the absence of that story, for people to kind of be aware that story needs to be told. That's If there was a compelling version of that story, it would be completely compatible with the dynamical approach, because the dynamical approach doesn't make any claims about the relationship between the two of them. It's sort of agnostic. All it's saying is there needs to be some story. That's yes.
So would you say that so you're saying that space-time does not curve around objects?
Well, no. So that's not quite right, because so I slightly avoided talking about the thing that I want to call space-time.
Okay.
But it seems reasonable. So this is not something that's in Brown's work, for example. But this seems like a sort of a quite natural extension. And this is the kind of thing that the philosopher Eleanor Knox talks about. When she talks about space-time, that what she has in mind is the structure that corresponds to what I kept calling the ontologically dependent metric.
Yeah.
And that ontologically dependent metric could curve as well. It could curve. It could have some really, really weird specific, it could be specified in a really, really weird way. And if you're willing to make that extra step to say, I'm going to call space-time the thing associated with that ontologically dependent metric, then yeah, absolutely, space-time is curved, and space-time is dynamical, and space-time is broken.
And then, so how would you explain, if you were to say, on one hand, okay, space-time is curved or it isn't curved, how do you explain that, something like gravitational lensing, what light curves around supermassive objects or whatever?
So we're all agreed that there's an object, what Tushar was calling the ontologically independent metric of general relativity, this object G, which looks mathematically like a metric field and which curves. So there's I guess the question is, when should we call that space-time?
Oh.
And it seems like a good answer, or at least the answer that someone like Eleanor would want to give, is only when it's read off by actual physical rods and clocks. Essentially, when this guy, the ontologically independent one, coincides with the ontologically dependent. Maybe that doesn't answer your question, but I think maybe that's...
But can I just add a little to what James just said? So you're talking about gravitational lensing, but what is it that happens in gravitational lensing? You've got some light source behind a large object, and the sort of the rays go in that direction, and they get bent back in, right? The story about what's happening is still a story about light, right? And so when we want to speak about sort of what's going on over there, we need things like this, things like Maxwell's equations, but in curved space-time. And it's not the case that what I was calling the ontologically independent field has nothing to do with that. In fact, it's a central component of those equations, right? So you have this large massive body, and that large massive body does affect the ontologically independent field by Einstein's field equation. That ontologically independent field does affect Maxwell's equations, but that final step to say, well, the sort of, as James was saying, the grid associated with the ontologically independent field is the same as the grid associated with the ontologically dependent field. That's the thing that we want to avoid saying. But we still have it's still completely consistent, a perfectly cogent story about what's really going on out there in the universe. We're realists about the ontologically independent field. We're slightly squeamish about sort of commitments to being realists about the ontologically dependent metric. Yeah.
So essentially, this just comes down to a framing problem. Is that what it is? Like, there's an object G, which we call space-time. It has some properties, but going with that math analogy that earlier, it essentially is how you measure it. You know, that space-time. Is that it?
Yeah, basically.
Okay.
Yeah, and it seems to be a widespread belief that rods and clocks must measure this guy, this G field, and that's what we're resisting. So a number of papers in the recent philosophical literature in the last couple of years have presented kind of baroque cases in general relativity in which your matter fields wouldn't survey this G field, which needs to be grist to the kind of mill that we're working at.
Yeah. Okay, so sorry to dig into matter fields again, so I'm a mathematician. Sorry about that. How do we think of matter fields? Do we think of them as things that we can curve and they can still be the same matter field? I don't want to get too technical. What's the topology of?
The way that, let's bracket the question of curvature. The way that we normally think of the fields in general relativity is you have a manifold and you have various, normally tensor fields sitting on the manifold. Some of these tensor fields will represent matter fields. Another tensor field, G, will allegedly represent space-time structure. This is the ontologically independent metric field that Tushar was talking about. This G plays the mathematical role of a metric field, metric tensor, whereas the rest of them don't necessarily. I don't know if this is useful.
Yeah, it is. Yeah.
And then these guys are coupled in various differential equations, which feature contracting the tensor distance.
Okay, so you don't want to posit a Riemannian metric on the manifold of the world if you don't have to.
Yeah, so that's a good way of saying it. So the claim would be in special relativity, you can get away with not having a Riemannian metric field eta, but in general relativity, you can't because of the existence of gravitational waves, etc., etc. But there's still a question of whether that's the guy that's surveyed by the matter fields or not. So, I'll try and summarize the two views in the context of special and general relativity. So, for the advocates of the dynamical approach, the metric field in special relativity is ontologically dependent upon properties of matter fields. And for that reason, it can't do any constraining or explanatory work in governing the behavior of those fields. Whereas for the advocate of the geometrical approach, the metric field, the Minkowski metric field in special relativity is ontologically independent, and therefore it can do constraining or explanatory work. That's the bit that we find, and Harvey as well finds, that at least needs more fleshing out to be convincing. In the general relativistic story, all parties are agreed that there exists an ontologically independent metric field. The question is whether it is surveyed, you might say, by rods and clocks. And advocates of the geometrical approach are going to say that necessarily it's surveyed by rods and clocks. Whereas the advocates of the dynamical approach are going to say that seems too strong, it depends upon contingent facts about how your matter fields are behaving, the kind of equations that are governing their motion, etc. So that's, and then you can think about the metric field which codifies the behavior of the matter fields. In that context, what Tushar called the ontologically dependent metric field. So another way of putting it would be that for the advocates of the dynamical approach, these two guys need not coincide, the dependent and independent metric fields, whereas for the advocates of the geometrical approach, they have to. But again, that latter claim is what seems suspicious. So the dialectic is somewhat complicated, but
yeah, sorry, you have had a question.
With these different, like geometrical versus the dynamical approach, do either one of them give a different idea of how time emerges, or like the arrow of time at all?
Short answer is no.
Okay.
The thing is, they're both sort of claims about things like the emergence of the arrow of time are claims that would presumably be made by physical theories themselves, or something that you might add to a physical theory. You might augment a physical theory in some way. So when you think about, for example, we think of the arrow of time as being having something to do with entropy, to measure of disorder or whatever. You might think, well, the arrow of time that's defined by that is the arrow that corresponds to is the time direction that corresponds to the increase of entropy. But then you need to posit something over and above that to explain sort of why there is the arrow, and you'd explain that by saying, well, at the beginning of time or whatever, the Big Bang, you had an area of extremely low entropy, and that caused the gradient, and blah blah blah. But that's an additional piece of technology that you're adding to physics. That's not what we're doing over here. So what we're doing over here is sort of it's philosophy. It's an interpretative game that we're playing over here. So we're trying to extract from the physics sort of things like ontological claims and things like explanatory claims, but sort of further facts that pretty much fall into the remit of physical theories are things that these discussions don't really touch.
Having said that, discussions of the arrow of time are like a huge part of philosophy and physics. So I don't know how much you know about this, but I would highly recommend David Albert's book if you haven't read it.
It's called Time and Chance. You had a
I was gonna say, so in quantum mechanics, right? There's a lot of theories that don't scale up or scale down when you compare to general relativity, right? So just because there's a conflict there doesn't mean that people call into question either one. So why, I feel like this is a similar scenario where there's two theories that are happening in different, not frames of reference, but different mediums. And so you guys are expecting there to be some type of explanation for why the behavior isn't working exactly the same way. But I'm more in the sense of why are you assuming that there needs to be that it needs to be explainable?
When you talk about two theories, are you talking about special relativity and general relativity? Sorry, James.
What did you mean by scale up and scale down as well?
Well, with quantum mechanics, the theories for how what it means to be matter is different than when you would approach something at a larger scale.
Right. So I'm sorry. Can you repeat your question, or less too short?
No.
I'm saying that just because there's a conflict between two different theories, there's no
So, I mean, I don't think we're really saying there's a conflict. I guess it's like you look at a particular theory, whether it be special relativity or general relativity or something else, and you try and work out what you should read off as being the ontology of the world from that theory, assuming that it were a complete story, or bracketing questions about other theories. So we can look at special relativity and we're like, oh, we shouldn't think that the metric field is something actually out there. General relativity should, but it's still a question of whether it's surveyed. So where's quantum mechanics coming into this?
No,
So-
I mean, maybe it doesn't relate to this, but I was just thinking that, so the special relativity and general relativity are something that's way more interrelated, so.
Yeah, and in fact the question of sort of how special relativity and general relativity are related is sort of deep and subtle and nuanced and interesting. But I think it's a different relationship than the relationship between sort of, let's say, general relativity and quantum mechanics.
Yeah, that's what I was.
Because special relativity and general relativity, by and large, so okay, take quantum mechanics and general relativity, they by and large make claims about sort of completely different length scales or energy scales. And we have sort of good reason to believe that in sort of relevant energy scales, they're both sort of completely sort of excellent theories, right? That's not quite what's happening in special relativity. So there are definitely claims that special relativity makes about particular length scales that conflict with claims that general relativity makes about the same length scales. And you go out and check which is the better theory. And it turns out that general relativity just is the better theory. So special relativity has been superseded by general relativity. The reason we're still interested in special relativity, well, one reason we're still interested in special relativity is because to a really, really good approximation, when the curvature in general relativity is pretty small, special relativity is approximately correct. Special relativity is just much easier than general relativity. So when dealing with sort of certain kinds of calculations, so for example, if we're calculating things about, for example, the light in this room, we don't really have to take into account the curvature, the curvature of the G field because of sort of all the matter present in this room. We can perfectly well treat this room as being completely flat, and you're not going to get any sort of noticeable deviations from what Maxwell's equations tell you there. So in that case, you know, that's the sense in which special relativity is useful. And similarly, in sort of philosophical discussions, as long as you're aware of the kinds of approximations that you're making, and as long as you're sort of at least cognizant of the ways in which special relativity is different from general relativity, you can use special relativity as a testing ground for kind of interpretative claims, and that's kind of what's happening here with the dynamical geometrical approach. And the reason that it's not exactly the same story that carries over to general relativity is exactly because there are certain things in the approximation of general relativity by special relativity that special relativity sort of necessarily just doesn't see. Having said that, you can carry forth an analog of the geometrical dynamical debate in both, and what's useful is sort of seeing the kinds of impact that you can have from one particular theory on sort of discussions in the other.
Yeah, so I would just add that, yeah, so actually there's two of the main sub-areas of philosophy of physics. One is look at a particular theory and try and understand what it's telling you on its own terms without looking at other theories. Another area of philosophy of physics is to see how does theory A relate to theory B, how do these guys mesh together. Often this latter project is more technical rather than metaphysical, but I think that they're both valid sub-disciplines of philosophy of physics. Yeah.
I have a less conceptual question for the both of you to answer. Just out of curiosity, what currently interests you most about your work?
Ooh, this is fun. Do you want to go first?
I think challenging accepted dogmas. So there's like, yeah, the dogma that matter must survey a particular object in your mathematical theory, and so it's quite satisfying to look at particular cases and really mull over whether that's the case. So, I mean, Tushar and I recently wrote a paper where we looked at the behavior of light in so-called Gödel spacetimes. These are really weird. They have closed time-like curves. It's possible to time travel in these spacetimes. They're It's super weird. But anyway, it turns out that light doesn't propagate as, in accordance with the structure of the G field in those particular cases, which is again, in support of the dynamical approach we think. So yeah, just challenging dogmas, I think, is a fun project.
Yeah, that's good. I second that. That's, I mean, so James and I work in sort of very, very, very similar areas and on very similar things, and turns out also write identical papers.
That's because our names are on there.
So yeah, that's basically it. So the other, for me, in addition to that, or maybe as a sort of kind of precursor to that, is what's really exciting is finally getting to do what I thought I was going to do when I studied physics. So if you look at popular science and popular physics especially, you look at sort of titles of books, and they always have words like reality, and there's a hidden reality, and road to reality, and whatever. And you think, oh, okay, well, this is what physicists do. I'm gonna go study physics, and I'm gonna learn how, I'm gonna figure out what the world is like, or at least I'll have a good idea of what people say the world is like. And then you kind of end up spending hours calculating scattering amplitudes in quantum field theory, and you go, this is not what I signed up for. And then you discover sort of why philosophy of physics is really exciting, is because you're allowed to, as James said, you're allowed to question dogmas, you're allowed to write weird papers where you say, take this space-time, and we're going to show you that in this space-time, light doesn't travel in the way that sort of everyone else says it does. So yeah, that's the fun about it.
So you might have heard this already. So I mean, in the philosophy of physics, people talk about a lot of different interpretations of quantum mechanics: the many worlds interpretation, the Broglie-Bohm interpretation, dynamical collapse interpretations. But people sometimes say that the interpretation that you study in the physics department is the shut up and calculate interpretation, which is somehow not as satisfying.
All right. Well, on that note, let's thanks James and Tushar for their presentation.